Hello friends, in our last discussion we talked about Gauss law for magnetic fields, which implies that magnetic monopoles do not exist. Then we discussed the Maxwell's equations, which summarize electromagnetism and form its foundation. In today's discussion we shall talk about magnetism of matter, which includes diamagnetism, paramagnetism and ferromagnetism. Magnets. The first known magnets were lodestones, which are stones that have been magnetized naturally. When the ancient Greeks and ancient Chinese discovered these rare stones, they were amused by the stone's ability to attract metal over a short distance as if by magic. Only much later did they learn to use lodestones and artificially magnetized pieces of iron in compasses to determine direction. Today, magnets and magnetic materials are omnipresent. Their magnetic properties can be traced to their atoms and electrons. In fact, the inexpensive magnet you might use to hold a note on the refrigerator door is a direct result of the quantum physics taking place in the atomic and subatomic material within the magnet. Before we explore some of this physics, let's briefly discuss the largest magnet we commonly use, that is, the Earth. The magnetism of Earth. Earth is a huge magnet. For points near Earth's surface, its magnetic field can be approximated as the field of a huge bar magnet, a magnetic dipole that connects the center of the planet. The figure here is an idealized, symmetric depiction of the dipole field without the distortion caused by passing charged particles from the Sun. Because Earth's magnetic field is that of a magnetic dipole moment is associated with the field. For the idealized field of figure, the magnitude of magnetic dipole moment is 8 into 10 raised power 22 joules per Tesla, and the direction of magnetic dipole moment makes an angle of 11.5 degrees with a rotation axis RR of Earth. The dipole axis, in figure, lies along magnetic dipole moment and intersects Earth's surface at the geomagnetic north pole of the northwest coast of Greenland and the geomagnetic south pole in Antarctica. The lines of the magnetic field generally emerge in the southern hemisphere and re enter Earth in the northern hemisphere. Thus, the magnetic pole that is in the Earth's northern hemisphere and known as North Magnetic Pole is really the south pole of Earth's magnetic dipole. The direction of the magnetic field at any location on Earth's surface is commonly specified in terms of two angles. The field declination is the angle left to right between geographic north, which is towards 90-degree latitude, and the horizontal component of the field. The field inclination is the angle up or down between a horizontal plane and the field's direction. Measurement of angles. Magnetometers measure these angles and determine the field with much precision. However, you can do reasonably well with just a compass and a dip meter. A compass is simply a needle shaped magnet that is mounted so it can rotate freely about a vertical axis. When it is held in a horizontal plane, the north pole end of the needle points generally towards the geomagnetic north pole. The angle between the needle and geographic north is the field declination. A dip meter is a similar magnet that can rotate freely about a horizontal axis. When its vertical plane of rotation is aligned with the direction of the compass, the angle between the meter's needle and the horizontal is the field inclination. At any point on Earth's surface, the measured magnetic field may differ appreciably in both magnitude and direction from the idealized dipole field as was shown in earlier figure. In fact, the point where the field is actually perpendicular to Earth's surface and inward is not located at the geomagnetic north pole of Greenland as we would expect. Instead, this so-called dip north pole is located in the Queen Elizabeth Islands in North Canada, far from Greenland. In addition, the field observed at any location on the surface of Earth varies with time by measurable amounts over a period of a few years and by substantial amounts over, say, 100 years. For example, between 1580 and 1820, the direction indicated by compass needles in London changed by 35 degrees. In spite of these local variations, the average dipole field changes only slowly over such relatively short time periods. Variations over longer periods can be studied by measuring the weak magnetism of the ocean floor on either side of the mid Atlantic ridge. This floor has been formed by molten magma that oozed up through the ridge from Earth's interior, solidified, and was pulled away from the ridge at the rate of a few centimeters per year. As the magma solidified, it became weakly magnetized with its magnetic field in the direction of Earth's magnetic field at the time of solidification. Study of this solidified magma across the ocean floor reveals that Earth's field has reversed its polarity about every million years. Theories explaining the reversal are still in preliminary stages. In fact, the mechanism that produces Earth's magnetic field is only vaguely understood. Magnetic materials. Each electron in an atom has an orbital magnetic dipole moment and a spin magnetic dipole moment that combine vectorially. The resultant of these two vector quantities combines vectorially with similar resultants for all other electrons in the atom, and the resultant for each atom combines with those for all the other atoms in a sample of a material. If the combination of all these magnetic dipole moments produce a magnetic field, then the material is magnetic. There are three general types of magnetism: diamagnetism, paramagnetism, and ferromagnetism. Diamagnetism. Diamagnetism is exhibited by all common materials, but is so feeble that it is masked if the material also exhibits magnetism of either of the two other types. In diamagnetism, weak magnetic dipole moments are produced in the atom of the material when the material is placed in an external magnetic field. The combination of all those induced dipole moments gives the material as a whole only a feeble net magnetic field. The dipole moments and thus their net field disappears when external magnetic field is removed. The term diamagnetic material usually refers to materials that exhibit only diamagnetism. The learning objective here would be that for a diamagnetic sample placed in an external magnetic field, identify that the field produces a magnetic dipole moment in the sample and identify the relative orientations of that moment and the field. And for a diamagnetic sample in a non-uniform magnetic field, describe the force on the sample and the resulting motion. We cannot yet discuss the quantum physical explanation of diamagnetism, but we can provide a classical explanation with the loop model of electron orbit as shown in this figure. This figure shows an electron moving at a constant speed v in a circular path of radius r that encloses an area A. To begin, we assume that in an atom of a diamagnetic material, each electron can orbit only clockwise as in figure D or counterclockwise as in figure B. To account for the lack of magnetism in the absence of an external magnetic field, we assume the atom lacks a net magnetic dipole moment. This implies that before external magnetic field is applied, the number of electrons orbiting in one direction is the same as that orbiting in the opposite direction, with the result that the net upward magnetic dipole moment of the atom equals the net downward magnetic dipole moment. Now let's turn on the non-uniform field as in figure A, in which external magnetic field is directed upward but is diverging. That is, the magnetic field lines are diverging. We could do this by increasing the current through an electromagnet or by moving the north pole of a bar magnet closer to and below the orbits. As the magnitude of external magnetic field increases from 0 to its final maximum steady state value, a clockwise electric field is induced around each electron's orbital loop according to Faraday's law and Lenz's law. Let us see how this induced electric field affects the orbiting electrons in figure B and D. In figure B, the counterclockwise electron is accelerated by the clockwise electric field. Thus, as the external magnetic field increases to its maximum value, the electron speed increases to a maximum value. This means that the associated conventional current I and the downward magnetic dipole moment vector mu due to I also increase. In figure D, the clockwise electron is decelerated by the clockwise electric field. Thus, here the electron speed, the associated current I, and the upward magnetic dipole moment vector mu due to I all decrease. By turning on external magnetic field, we have given the atom a net magnetic dipole moment that is downward. This would also be so if the magnetic field were uniform. The non-uniformity of external magnetic field also affects the atom because the current I in figure B increase, the upward magnetic forces in figure C also increase, as does the net upward force on the current loop. Because current I in figure D decreases, the downward magnetic forces in figure E also decrease, as does the net downward force on the current loop. Thus, by turning on the non-uniform external magnetic field, we have produced a net force on the atom. Moreover, the force is directed away from the region of greater magnetic field. Here we have argued with fictitious electron orbits, that is current loops, but we have ended up with exactly what happens to a diamagnetic material. That is, if we apply the magnetic field as shown in figure, the material develops a downward magnetic dipole moment and experiences an upward force. When the field is removed, both the dipole moment and the force disappear. The external field need not be positioned as shown. Similar arguments can be made for other orientations of external magnetic field. In general, a diamagnetic material placed in an external magnetic field develops a magnetic dipole moment directed opposite If the field is non-uniform, the diamagnetic material is repelled from a region of greater magnetic field towards a region of lesser field. Paramagnetism. In paramagnetic materials, the spin and orbital magnetic dipole moments of the electron in each atom do not cancel but add vectorially to give the atom a net and permanent magnetic dipole moment. In the absence of an external magnetic field, these atomic dipole moments are randomly oriented and the net magnetic dipole moment of the material is 0. However, if a sample of the material is placed in an external magnetic field, the magnetic dipole moments tend to line up with the field, which gives the sample a net magnetic dipole moment. This alignment with the external field is the opposite of what we saw with diamagnetic materials. So, the generalization is a paramagnetic material placed in an external magnetic field develops a magnetic dipole moment in the direction of external magnetic field. If the field is non-uniform, the paramagnetic material is attracted towards a region of greater magnetic field from a region of lesser field. A paramagnetic sample with n atoms would have a magnetic dipole moment of magnitude n into mu if alignment of its atomic dipoles were complete. However, random collisions of atoms due to their thermal agitation transfer energy among the atoms, disrupting their alignment and thus reducing the sample's magnetic dipole moment. Ferromagnetism. When we speak of magnetism in everyday conversation, we almost always have a mental picture of a bar magnet or a disk magnet. That is, we picture a ferromagnetic material having strong permanent magnetism and not a diamagnetic or paramagnetic material having weak temporary magnetism. Iron, cobalt, nickel and alloys containing these elements exhibit ferromagnetism because of a quantum physical effect called exchange coupling, in which the electron spins of one atom interact with those of neighboring atoms. The result is alignment of the magnetic dipole moments of the atoms in spite of the randomizing tendency of atomic collisions due to thermal agitation. This persistent alignment is what gives ferromagnetic materials their permanent magnetism. Thermal agitation. If the temperature of a ferromagnetic material is raised above a certain critical value called the Curie temperature, the exchange coupling ceases to be effective. Most such materials then become simply paramagnetic. That is, the dipoles still tend to align with an external field but much more weakly, and thermal agitation can now more easily disrupt the alignment. The Curie temperature for iron is 1043 Kelvin. Magnetization. The magnetization of a ferromagnetic material such as iron can be studied with an arrangement called a Rowland ring. The material is formed into a thin toroidal core of circular cross section. A primary coil P having n turns per unit length is wrapped around the core and carries current IP. The coil is essentially a long solenoid bent into a circle. If the iron core were not present, the magnitude of the magnetic field inside the coil would be B0 is equal to mu 0 into IP into N. However, with the iron core present, the magnetic field inside the coil is greater than B0, usually by a large amount. We can write the magnitude of this field as B is equal to B0 plus Bm. Here Bm is the magnitude of the magnetic field contributed by the iron core. This contribution from the alignment of the atomic dipole moments within the iron due to exchange coupling and to the applied magnetic field B0 is proportional to the magnetization M of the iron. That is, the contribution Bm is proportional to the magnetic dipole moment per unit volume of the iron. To determine Bm, we use a secondary coil S to measure B, compute B0 with equation A and subtract as suggested by equation B. Figure shows a magnetization curve for a ferromagnetic material in a Rowland ring. The ratio Bm upon Bm maximum, where Bm maximum is the maximum possible value of Bm corresponding to saturation, is plotted versus B0. The curve shows the extent to which an applied magnetic field can align the atomic dipole moments of a material. So friends, this brings us to the end of our discussion in this lecture, and therefore we sum up. Earth is approximately a magnetic dipole with the dipole axis somewhat off the rotation axis and with the south pole in the northern hemisphere. Diamagnetic materials exhibit magnetism only when placed in an external magnetic field. There, they form magnetic dipoles directed opposite the external field. Paramagnetic materials have atoms with a permanent magnetic dipole moment, but the moments are randomly oriented with no net moment unless the material is in an external magnetic field where the dipoles tend to align with the field. The magnetic dipole moments in a ferromagnetic material can be aligned by an external magnetic field and then, after the external field is removed, remain partially aligned in regions. So that is it for today. See you in the next lecture with more on electromagnetism. Thank you very much.